Viewer discretion is advised.
Imagine you're sitting in your car, in the passenger seat. All there is to do is look out the window at the trees flying by.
You automatically disregard the notion that the trees are actually moving because you know that you're moving, as the car's engine shoots across the highway.
Would you think I'm crazy if I told you that I don't remember what I was going to say?
So would you think she's crazy if she told you that in reality, the trees are actually moving? Well, they are. They're moving at a negative velocity because in relation to you, they are moving backwards.
Sure, it's hard to digest at first, but just give us a few moments of your time and we will attempt to clear things up to the best of our ability.
Alright, so Albert Einstein's my dad, so you won't have to leave this room until you understand this, the theory of special relativity. Alright?
I hope you like getting your mind,
Sala.
because that's exactly what's going to happen.
Breathe so slowly into hearts of men who need more than they get. Daylight needs
Save yourselves.
Showing that utter weirdness was to showcase the fact that the theory of special relativity can get relatively dense mathematically. So we'll try to dive into the concept without, killing you all.
First, we should address what the theory of special relativity is. Back in his heyday, Albert Einstein pondered the constant speed of light. Thanks to Albert Einstein, we know that no matter what the velocity is, the speed of light stays the same.
In order for this to hold true, which it has to, since it is true, right? Two factors come into play: time dilation and length contraction.
There's a fairly well-known equation they might remember from high school, and that is velocity equals distance divided by time.
In this example with a car, it is physically possible to change a velocity. However, that's not the point. The point is, if we're dealing with a light instead of cars, the velocity couldn't possibly change, showcasing the fact that if the distance changes, then the time must change as well, in order to maintain a constant speed of light.
In order to prevent objects from traveling the speed of light, which according to the famous equation E equals mc squared is impossible for any object with mass to do, time dilation and length contraction come into play. Perhaps now you can see why this is the case, based on the example about the car we provided. If you don't understand it yet, well, maybe you will before the end of the video. Let's just see what happens.
It's all about the observer, who's observing and who's actually in the rocket. There is a complete difference in experience between the person piloting the rocket and a person standing on a floating asteroid watching the rocket. To prevent this rocket from moving at the speed of light, which is impossible for anything with mass to do according to E equals mc squared, which is another property or condition of the theory of special relativity, which we won't really touch much upon in this video. In order to prevent that from traveling the speed of light, what's going to happen is that the length of the rocket will be smushed. Is this rocket actually stretching? No, Disney World reference. So, yep, it's squished, and that's so that the distance or length, which are the same thing, of the rocket will be smaller so that it cannot travel as much distance in a certain amount of time, which would make it past the speed of light or reach it, because that is physically impossible.
That is length contraction for you folks. Time dilation is not a topic that our video is about. That may be relatively easier to understand than length contraction. We have two visuals for you about this one.
Pretend that this kid is a rocket ship traveling really fast. As this rocket ship approaches the speed of light, time will slow down for the ship and all those aboard it in order to make sure that it cannot travel a certain distance in a certain amount of time. The people aboard the rocket ship will not feel as if they are moving in slow motion. They will feel normal, but observers outside the ship will see what is happening.
You can test this out right now, like we're about to. It's going to blow your mind. You're about to see that everything's relative. Nothing is absolute, besides the laws of the universe such as the constant speed of light.
The object moves up and down in a straight line. Rachel tossed up the object in the same way she did before, except for this time, as observers, the object is not moving straight up. Its path forms an isosceles triangle.
Thank you for taking time to watch our video. Hopefully you aren't confused or tired. If you are, well, at least the video is over.